Hello everyone and welcome. This is the second half of the part 3 lecture on phases and properties of liquids. We're going to start with the definition of the term viscosity. You've probably heard this term before, often used to describe very thick liquids like honey or molasses. So the definition of viscosity is a fluid's resistance to flow. So again, note it is a fluid's resistance to flow. So this means that substances that have stronger IMFs will have higher viscosities. Why? Well, again, remember that intermolecular force strength is related to both molecular size and shape, and viscosity is as well. Viscosity is also temperature dependent. Usually, viscosity decreases as temperature increases. Why is this? Well, again, let's think about how this term here, viscosity, represents a fluid's resistance to flow. So when you think of the word viscous, you typically think of very thick liquids, again, like honey or molasses or like motor oil, right? These are liquids that are very thick, they're very viscous, they have high viscosities, they are very resistant to flowing, right? You tip open a bottle of honey or molasses and it drips out really slow, whereas a liquid like water, which has a fairly low viscosity, right? You tip open a bottle of water, the water comes pouring right out into the glass below. So this would have generally has kind of a low viscosity, and I'll break down the reasons for this why in a minute, because you might be a little confused about this idea here where IMF is related to viscosity. Now, the second point down here, viscosity being temperature dependent, where it says usually viscosity decreases as temperature increases. Why? Well, think about again what viscosity is. It's a resistance to flow, right? And so something like honey, where we have these big molecules that are very attracted to one another, the liquid is viscous because these molecules like to stick together. They don't pull apart very easily, and so the liquid's not going to flow as easily as, something like water. Well, then what happens if we heat this object up? If we heat it up, these molecules are going to be moving more quickly. They're going to be moving with more kinetic energy, so it's easier for them to separate from one another, and the liquid will flow more easily. Thus, viscosity would decrease. So we have an inverse relationship here. Viscosity decreases as temperature increases. All right. Now let's consider the IMFs involved in the following three regions of the liquids shown here. So this is a diagram where we're just looking at, the molecular breakdown of, let's just say, a glass of water. So the glass walls of the container are on the side here. Glass is typically made of silicon dioxide, so those are the green spheres. Those are the SiO2 molecules. Then the gray spheres in the middle here represent water molecules. So we've got three regions to consider. First, within the liquid itself, so how does a water molecule interact with nearby water molecules? Then, second, at a surface at which there is no attractive force from the outside of the liquid, so say here, where these water molecules are attracted to the water molecules within the liquid, but they're also on the outside and they're not attracted to the air molecules or whatever the atmospheric conditions are here surrounding those water molecules. And then finally, number three, at a surface at which there is an attractive force from outside the liquid. So these water molecules that are on the outside, but they're up against the glass. So they're attracted to, again, the water molecules within the water itself, but they're also attracted to these SiO2 molecules. Since the silicon dioxide, we're going to have those oxygen atoms will have some lone pairs that the water molecules will be attracted to. Okay, so let's start then with surface tension. So we're going to break down each of those three regions as it relates to, first, surface tension. So surface tension is the energy required to increase the surface area of a liquid by some amount. Essentially, it is the liquid's resistance to having its surface deform. So this is showing, well, as we'll see in a minute, this is like the long leg of an insect, like pushing down on the surface of a liquid. So again, that surface tension is the water's resistance to having its surface deform. Basically, how much energy do you have to push down on the water with to cause the shape of the water to deform and bend, basically, to break the surface. So because the molecules at the surface of a liquid are in contact with fewer other molecules, right? So think about that first region. Think about these water molecules right here. They're in contact with the outside environment, and they're also in contact with water molecules within the liquid itself. But because, they are kind of split in half, right? Half of the molecules they interact with are probably air molecules from the outside. Half are the water molecules from within the inside. We're saying here that they are in contact with fewer other molecules, right? They're in contact with, 5 other molecules in this diagram, whereas a water molecule in here is got, 8, 10, however many water molecules directly surrounding it. So what's going to happen here is the liquid is going to contract. So when some amount of energy is pushed down on the surface of the water, these water molecules have a tendency to contract. They have a tendency to retreat closer to, they pull inwards towards the water molecules that they are attracted to, and they pull away from the outside environment that they are not attracted to, right? So think about it. This water molecule is not attracted to these molecules, but it is attracted to these molecules. So if you push down on the water, its natural reaction is to retreat inwards towards the molecules that it is attracted to. So this is a big reason why water has such a high surface tension. These inner molecules are attracted to one another, so they're pulling in all directions. These outer molecules are also pulling inwards, and so the surface resists having its basically tension broken. It resists having its surface broken because these water molecules want to retreat inwards towards the other water molecules. So water has a fairly strong or fairly high surface tension, we would say. So this is what enables insects such as the water strider to walk across the water's surface. So that's what this short video is right here. Let me turn the volume off there. You can see these are water striders. You've probably seen these little bugs before. So they're very low weight, and they have these very long legs. So their weight is evenly distributed across the surface of the water, and they actually push down on the water with such little force that they don't break the surface tension of the water, and they can kind of stride or kind of like skitter right along the surface of the water. Okay. So next then, let's further analyze surface tension and how this causes what's called capillary action. So again, the surface tension is occurring here at 2, right, where the water molecules retreat inwards, away from, the downward force of the atmosphere or whatever is pushing on the surface of the water. This causes a polar substance such as water to draw upwards. Why does this occur? So this effect, again, is called capillary action. This surface tension here at 2, when you push down on water, this tends to draw a polar substance, so again, normally water, this tends to draw it upwards. It tends to draw it up the tube. This effect, again, is called capillary action. This increases as the diameter of the cylinder decreases. You can see this at the photo here in the bottom right. So again, this increases as the diameter of the cylinder decreases. So we can see as the cylinders get wider, going from left to right here. So we have a thin cylinder, and then they're slowly getting thicker. See here with the thin cylinder, the green liquid is farther up than it is with these 2 cylinders. So this capillary action results from 2 forces. First, cohesion. So these are the attractive forces between molecules of the same substance. So this occurs here in region number 1. So between these water molecules, these molecules are attracted to one another. This also occurs here again at number 2, where we're describing that surface tension force. This water molecule, or these water molecules on the outside, are attracted to the molecules on the inside. So they tend to draw downwards into the other water molecules. We also have a force called adhesion. So adhesion, this describes the attractions between molecules of different substances. So like an adhesive, a glue. This is when you can glue 2 different things together. So adhesive forces are the attractive forces between molecules of different substances. So like region number 3, where we've got these water molecules which are attracted to the glass walls of the container, those silicon dioxide molecules. So we have attractive forces here in the middle, which tends to draw the water down. And we have the attractive forces on the outside, which tends to draw the water on the outside up. And so thus we get that capillary action. The water will go up the outside of the container because of the adhesive forces, and then it kind of is drawn in the middle because of the cohesive forces. All right, so when adhesion is greater than cohesion, so when those attractive forces on the side are greater than the attractive forces in the middle, the liquid will be pulled up the cylinder, and a concave meniscus is formed. So adhesion, this is when water or whatever the liquid is more attracted to the glass than it is to itself. So the surface is concave and the liquid tends to draw up the tube or up the cylinder. When cohesion is greater than adhesion, the liquid will stick to itself more and form a convex meniscus. So a good example of this is mercury. Mercury is more attracted to itself than it is to the glass. So we have cohesion, and so here the liquid tends not to draw up the cylinder as much, and we get this interesting convex meniscus here, where the mercury, again, is more attracted to itself than it is to the walls of the container, and so we get this convex meniscus. Okay, quick knowledge check. We have 4 molecules being shown here: diethyl ether, acetone, ethanol, and ethylene glycol. These are similar to, or these are the liquids we saw earlier in the unit when we were looking at how intermolecular forces affects the phases of liquids. So you can see the surface tension of these liquids shown in this column in the table, and their viscosities are shown in this column in the table. So I'd like you to pause the video and try for a minute to answer this question. Explain the differences in surface tension and viscosity for these 4 liquids in terms of their size, their shape, and their intermolecular forces. Okay, and the correct answer here, or the way you'd want to explain this, is you're primarily going to be thinking about the intermolecular forces here. So these molecules have generally a fairly similar size. Diethyl ether is a little bit bigger, but generally we've got similar sizes and similar molar masses here. So surface tension the difference here in surface tension, so the general increase in surface tension as we go down the column and the clear increase in viscosity as we go down the column can be best explained by the difference in the intermolecular forces. Diethyl ether is polar, acetone is also polar, whereas ethanol, ethylene glycol have hydrogen bonding. So we can see these two are going to have the stronger intermolecular forces, so they generally have stronger surface tensions, especially ethylene glycol, and they clearly have stronger viscosities. So that's the type of answer I would expect here, is you to just be able to recognize the intermolecular forces present and note that surface tension and viscosity generally increase as intermolecular force strength increases. You may be wondering here why acetone appears to have essentially the same surface tension as ethanol, despite acetone being polar and having dipole-dipole interactions, whereas ethanol would have hydrogen bonding. Now you can see a clear difference in their viscosity, but surface tensions are almost identical. Why is this? This is a unique exception. This is not something I would expect you to know on the exam. Acetone here, acetone is a very planar molecule. It lies very flat. So because it's such a planar molecule, it actually stacks very efficiently, which causes its surface tension to be oddly high relative to the strength of its intermolecular forces. So that's the reason why acetone has an oddly high surface tension relative to its size and intermolecular force strength. You can see the difference is a bit more pronounced when we compare the viscosities of these 2 molecules. All right, next let's analyze these 2 terms, hydrophilic and hydrophobic. So we are going to continue to use the concepts of polarity and intermolecular forces to predict how a given compound is likely to interact with water, since note the prefix hydro in both of these terms. So starting with the first term, hydrophilic, a compound which readily interacts with, which means it is happy to mix or dissolve with water. These compounds are called hydrophilic, which kind of means water-loving. So hydrophilic, these are compounds that readily interact with water. Compounds which do not interact, mix, or dissolve well with water are called hydrophobic. So, right, think of the term phobia, meaning fear. So hydrophobic refers to compounds that are, quote, water fearing. They do not interact, mix, or dissolve well with water. Because water is very polar, it often will easily interact with other polar molecules. So polar molecules tend to be hydrophilic. Conversely, nonpolar molecules generally do not interact well with water. So nonpolar molecules tend to be hydrophobic. Let's look at some visual examples using those functional groups we touched on a little bit at the end of the intermolecular forces lecture. So let's try and predict whether they are likely to be hydrophilic or hydrophobic. We'll start with these first four. So we grouped these first four together as having similar intermolecular forces. So again, I'd like you to pause the video and try and predict, will these first four functional groups, alkanes, alkenes, alkynes, and benzene/phenols, are these likely to be hydrophilic or hydrophobic? Okay, and the correct answer here is hydrophobic. These first four contain dispersion forces. They contain only non-polar bonds because they typically have carbons and hydrogens only. These are likely to be hydrophobic. Next are these four. So these four we group together. They have hydrogen bonding. They have polar groups, which means they can give and receive H bonds from water. They are going to be hydrophilic. They will readily interact with and dissolve or mix with water because of their hydrogen bonding. And finally, these four, the aldehydes, esters, ketones, and ethers. These, remember, we group them as having dipole-dipole interactions. They have polar groups. They can receive hydrogen bonds from water, and so we would expect them to be somewhat or potentially fully hydrophilic, depending upon the lengths of the carbon chains attached to them. They are likely to be hydrophilic. Okay, now let's relate IMF strength to some observed properties. So, reviewing. As IMF strength increases, remember that boiling point will increase, so higher temperature / more energy is needed to overcome the IMFs holding the particles together in the liquid phase. Melting point will increase, so again we need a higher temperature / more energy to overcome the IMFs holding the particles together in the solid phase. Solubility in water will increase, so now we see that stronger or typically more polar IMFs allow for hydrogen bonding with water, and if you can hydrogen bond with water, you are likely to be soluble in water, which means you are hydrophilic. If you are nonpolar, you are likely to not be soluble in water and you will be hydrophobic. So for example, like oils, a lot of oil products are typically just these long carbon hydrogen chains. They are usually nonpolar, so they're not soluble in water. They are hydrophobic, so that's why, if you've ever seen images of an oil spill occurring before, the oil tends to just sit on the top of the water. It doesn't mix with the water because it's hydrophobic, it's nonpolar. Okay, and summarizing this, IMF strength increases, boiling point, melting point, all of your molar heats increase, your solubilities increase, and then remember that the effects this would have on viscosity, vapor pressure, etc., the other properties we have analyzed up to this point. Okay, let's go through a few practice problems. So practice number 1. Which requires a higher temperature to melt, molecule 1 or molecule 2? So again, pause the video, give this one a try. Okay, and the correct answer here is molecule 2. So molecule 1 and molecule 2, notice they are both carbon and hydrogen only. They are both non-polar alkanes. They have dispersion forces only. If you're comparing two molecules where the strongest IMF is the same, especially with dispersion forces, the molecule with the higher molecular weight will win, so to speak. So molecular 2 is bigger, it's going to have the stronger dispersion forces and thus the stronger intermolecular forces, and it will thus require a higher temperature to melt. Alright, next, these two molecules. Pause the video, give them a try. Okay, Now if we go through these molecules, we see molecule 1 has hydrogen bonding. It's got an OH group right here. Molecule 2 looks like nonpolar only. So molecule 1, hydrogen bonding. Molecule 2, dispersion forces. Molecule 1 is going to have the stronger intermolecular forces, and we would thus expect molecule 1 to have the higher boiling point. And so the final answer here would be that molecule 2 has the lower boiling point. Molecule 2 has the lower boiling points. Okay, one more problem for you. I think I might have one more after this, but practice number 3, which would be more soluble in water, molecule 1 or molecule 2? Okay, so let's go through this and let's analyze. Again, solubility in water generally depends on IMF strength, particularly which type of IMF you have. So molecules 1 and 2 both have phenyl groups. Those are the 6-carbon rings. Molecule 1 has an alcohol group, whereas molecule 2 has an alkane attached to it, a CH3. So this one right here can hydrogen bond. This one's going to have dispersion only. Molecule 1 therefore has the stronger IMFs. It's more polar with its hydrogen bonding. Molecule 2 has weak IMFs, dispersion forces only. So we would expect then molecule 1 to be more soluble in water. Okay, that was actually all 3 of the problems I had. Here are a few additional practice problems. These are taken from the OpenStax textbook, but if you need a little more practice on anything covered in this lecture or in the first half of the lecture, please go ahead and give these problems a try. And then here on the next slide are the answers, so pause the video now if you don't want to see the answers. Alright, and here are the answers to those problems. That's the end of this lecture on the phases of molecules and the properties of liquids. I will see you in the next one when we learn more about heating curves.